Hi, my name is Holger. I'm product manager for durability for Testlab Neo, and so I will show you a bit about Testlab Neo and the process designer, how you can make use of it for anomaly detection.
My name is Raj Ipili. I'm in the Simcenter Test support team. Shall I give a brief background here, Holger?
Yeah, if you want to, please do that.
Yes. Okay. This webinar, as the name suggests, is on anomaly detection during data acquisition. Many times we collect data using accelerometers, microphones, and unwantedly something may happen. There can be one accelerometer that could fall down, which we may not notice during the time of data acquisition, but we may find out later when we are analyzing the data. So this webinar is focused on identifying when some of these anomalies happen in the data. So there can be some things like spikes that can happen in the data, and then there is sometimes drifts in the data that can happen. These are common issues that we encounter during regular data acquisition. So this webinar will be focused on how to identify that and not just know that there is an anomaly, but we'll also show how to use this anomaly detection while we are taking the data, so that immediately after an acquisition, you'll get a report that things look okay or not. That way you can immediately check whether there is an issues with the data rather than finding a few days later. So in that regard, this whole webinar is broken down into two parts, I would say. First will be presented by Holger, where he will go through the different methods or the process we use to identify these anomalies. Then later, I'm going to use that same process to simulate data acquisition, where we will simulate an anomaly and then see whether the tool helps us in detecting that or not. This is all based in Testlab Neo platform. In Testlab Neo, for acquisition, there is time data acquisition, and for this anomaly detection, there is a process designer. And there are different methods available in Neo that can help us with this. And Holger will take us through that. Holger?
So then I will start. Basically, if you ever have looked for anomalies in your measurements, probably figured out that there's no silver bullet in finding it. One man's anomaly is another man's perfect measurement. By just looking at the data, at the signals, as you see it here in my screen, just looking at them, it's very difficult to really clearly say, this is an anomaly, this is a spike, this is something that is wrong. If you don't know what the measurement was about, if you don't know about the component, if you don't know what was the expectation. Basically, we have here a couple of checks, but the main idea is that we cannot come up with a perfect check for everybody. But we can come up with a process that has certain methods to check certain anomalies, but you can still change the parameters and make sure that it's fitting exactly to your case. And we will see, if we go through the different checks, we will see that obviously some of them, they detect a certain fact, like let's say there's a check for a flat line or a constant signal that is always at the same value. Now, if you measure a certain event like a gear channel, and in a certain measurement the gear doesn't change, so that's a perfect measurement. It's not an anomaly. It's really about what you expect from your measurement compared to what you see in the measurement. And the biggest problem is you have a lot of measurements, you have maybe a lot of channels, and you have to dig through all of them to get this information. And this is where this process can help you. This now is Testlab Neo. It has some more features. You will find things that you already know, like the display area here. You see here something, I've selected the throughput file, and you see the list view with the channels. In the middle, there's the process area, and on the right side, you see all the methods that we have available for processing. In Neo, we have a thing which is really handy that is called the pivot table. And basically, the pivot table, there you can just look at data by having a table where on one side you see, for example, the job ID, and on the top you see the function class. So in this case, it's only time. But the nice thing is it doesn't work only on one level. It also works on all folders below. So it's recursively going through all the folders. So if I click on the run, I now not only see the time domain, I also see some statistics, hardware checks, auto powers. If I want to click on it, it's like in the list view. If you click on something, you will see the data. And you can even do this for the full section. So the table doesn't get more messy, but you will see that there are more data or more numbers. Basically, the number says how many channels are in that cell. And there's a whole bunch of different configurations you can use which fit to your application. And you can define whatever attribute you want to see. So for example, I can use the DOF ID versus run. So I see the whole section, and then you have a nice table where on this side you see all the channels, and on the top you see all the runs. Or, which will later be very handy, we have something like DOF ID versus creator. Creator is the method that has created the data. And these are basically the same names you see here in the process. So it's really up to you to give them the right name. And it's here now very easy to select certain results for certain checks. This is something which is maybe new for you if you all work with Testlab Classic, but it's a very nice feature in Testlab Neo. And in this webinar, I will make a lot of use of it because it really makes it easy to select what you want. Now, let's first look at the process. It might look a bit overwhelming, it's big, but nice thing is it's there. It's in the installation of 2506 Service Level 1, and you can just pick it up from there. But it's not an implementation that was done as a specific method. So we didn't implement it specifically for anomaly check. We just used the methods we have to make sure we implement the detection that we needed. We still can change the parameters, and you still can change, or we can add more methods if you want to. Here you see that's the input method. This is where every data that are selected in the input basket enters the process. And then I can have some global way to select channels or block channels. And then all of these channels then go into all the checks. And every check is basically one line here. So we have a hardware check, we have a spike check, we have a flat line check, we have drift and pass check. So every line is basically one check. And you can enable or disable the checks. And here you also see how these checks in practice work, and where you can change the parameters if you need to. In the end, every line here will output the indicators into that global method here. And if you select the results, you will have this nice table of all the results, and you will have a nice table indicating where a problem is. And this indicating where a problem is organized in a way that it's a nice overview where you can easily spot where the problems are. So for this, I used the numbers 111 for everything is okay. It's visually less striking. And then I use the number 888 if there's a problem. So if you look at this big table, and then basically you have to focus on everything that is 888, because this says this anomaly check has detected the problem or has detected a certain issue. Now let's go through the whole table of checks. The first check is the hardware check. While doing the measurements with our measurement instruments, if there's a problem, it's also recorded with the data. So you can look at the data. Maybe you already saw that if you right-click on a throughput data, you get a small text file saying in a certain channel, in a certain time segment, there was a problem. There was an overload. There was some kind of problem. Here we have the way to pick that up, and the hardware check, this is basically the method that picks it up. And if I look at the parameters, you see that I can select what kind of checks I want to consider. So in my case, I didn't consider the GPS problems. If there would be one, I ignore that. You can also activate it, of course. And then here's a list of all the problems that can occur while in measurement. For me, it's not important which problem it is. I want to have everything, but you can sub-select here and just select the problems you want to detect. And once you did that, there will be an output is one time signal that indicates when in time there was the problem. So if you check this time signal later on, you will see, okay, from 10 to 12 seconds, there was a problem. And then this is a segment of your measurement you might double check, or you want to make sure that the data there is still okay. So that's the first check. The next check is the spike filter. Here we basically have a method that corrects the spike already with a certain set of parameters, but I don't want to correct it immediately. I just want to know where it is so that you have the chance to compare it and to look at it and decide whether it's really a problem or not. So this is what I do in the next methods. But what is the spike filter actually doing? Let's go to the manual. So this is the manual for the spike filter. And here we have an example of the input data with some disturbances, some anomalies. The output of the correction would be really a signal where this is removed. Now, how is that done? In a first step, we calculate the absolute differences of consecutive sample points. So the difference between two sample points that are following each other. And this gives us another time signal like this here. So there's usually rather small differences, but then at some point there are bigger ones. These obviously are the ones where the spikes appear. So this is the first step. We calculate the differences between samples. Then we calculate the standard deviation of that signal. And then we allow the user to enter a threshold factor, and we multiply the standard deviation with this threshold. That gives us here a line. And then everything that is above that line indicates here we have a spike. So here you see maybe in this area we saw these are spikes, maybe the others are as well. And then additionally we define a spike is usually a small instance. The spike doesn't occur over 1 second or 2 seconds or 10 seconds. Then you might have a different problem, but it's not a spike. So we also look how long the signal is above that threshold, and you can enter the number of samples you want to have as a maximum length. In my case, I used 11 samples. If it's below 11 samples, then it's detected as a spike and it will be corrected. If it's longer, it will not be considered as a spike. And if it's a spike, then it will be corrected. And you see here, it's basically using the last point before the spike, which is valid, and the first sample after the spike that is valid, and just does a linear interpolation. That might be okay for your case, depending on what you're doing. It might be not good enough. That's one of the reasons why we don't do it as a correction right now. We just figure out where the spike is. And maybe in your case, it would be better to just remove that segment instead of trying to have a linear interpolation. The next check is a flatline detection, and flatline means it's not the full signal, it's only one segment with a certain length. In my case, it's 5 seconds. Here's an example of such a signal. You have something which is purely okay measurement, and then at some point in time, really the value doesn't change anymore for a certain period of time. And then it starts again. So it's some kind of a dropout, a flat line. But if you look at the full signal, you maybe don't see that exactly because it's hidden and it's maybe just a short period of time. So in my case, I will check for those if they are longer than 5 seconds. But if you want to change that, you can just go into this method here and change this 5 to 2 or 10 or whatever. So it's really up to you to change. Oh, maybe I should 5. It's really up to you to change the parameters and adapt it to the cases and to the measurement as you expect it. It's okay if it's dropping out for 2 seconds, then put it to some higher value. The next check is the drift check. Again, we have here the drift correction. The method again does the correction, and we use the same trick. We take the corrected signal and the input signal and just build the difference to indicate where the change has happened. Again, drift correction, I go to the menu and it explains how it works. I have the input signal. In the first part, 1 to 5 seconds, that's another parameter. It calculates the mean value also for the last part of the signal. And then basically it will correct the signal to make sure that the value here, the mean value of the ending, is shifting upwards, and it's shifting basically everything up, so it's really a linear shift. Point on the left will remain at the same position, so it's not moved to 0, it keeps the position where it is. And on the right, this one will then be on the same level. So by this, the correction is done. We have also a nonlinear drift correction. I didn't use it here in the process yet, but if that makes sense for your case, it's also possible. However, it's also more difficult to configure because you have to make sure that the nonlinear drift, it's a bit more complicated to make sure that it's not catching up on any high frequency phenomenon that you want to measure. For now, I will just have the linear drift correction or the linear drift detection. And basically, as I said before, you can define the parameters. So how big is this interval in the beginning and the end? And here I will only see a detection whether this has triggered for a drift or not. So next, We also have some methods that just use statistical values of your input signal and compare it and see whether there's an anomaly. But as I also said, it's much more meaningful to not only compare statistical values, but also to compare it to your expectation. So how can you enter your expectation into the process? We have in the time data acquisition software, there's a field called limit EU, limit engineering unit. You can either enter a limit engineering range, or which is then upwards and downwards is symmetric to 0, or you can enter the values upper and lower limit individually. But this is really something where you put in your expectation. You think that this channel, this acceleration channel, should be between -5 and +5 G, or it's between minus and plus 10 G, whatever. But define that up front, and then later on we can compare whether the measurement actually was in that range, or whether it was much too high, or whether it was much too low. So these checks only make sense if you enter this limit EU. For example, if you have data from other front ends, from external import, like RPC3 files or some other mechanism, then usually you don't have that data, and then basically you would switch it off. This can be done easily by just clicking here, and then you would switch off this complete check. In my case, I have these values, and then basically here statistics are calculated, the limit EU values are calculated, and then I will do the check. And the checks basically are, one is called overrange. The overrange checks whether you use more than 90% of the limit EU range. You have a certain range and it's really almost completely used. That might be okay. Then you can increase the percentage. But this is an indicator that maybe you are too close to the border. Under range is the other way around. If you have a certain range and you don't use it at all, so the actual range is below 1% of the limit EU range, then you maybe have a problem with the precision, or at least you have a problem with your expectation. The final one is the improper header, where the maximum or the minimum is even outside of this limit EU values. The way we store our data, this doesn't lead immediately to the clipping of your input signal. So even if you have that improper header, and then you will see that still the measurement is okay. In some other measurement systems, you would see that it's then hitting the ceiling and then just being flat for a certain amount of time and then coming back. In our system, that usually isn't the case. You can still store the data that is larger than limit EU up to a certain point, but there's enough headroom. Still, it's a good idea to know whether it's happening or not. And the next check is basically on global statistics without any further knowledge. These are rather simple checks, but also might be helpful in some cases. So one would be, if you have a dead signal, it means the maximum is equal to the minimum. So there's no change at all over the full signal, in the full signal. Then there's a check called unipolar, where if the maximum multiplied with the minimum is bigger than 0, then basically you only have positive values or you only have negative values. And if that is the case, well, if you have an acceleration in most of the measurement, it would be strange. If you have a speed channel, like a velocity of a car, if you have an RPM channel that is going only in one direction, that is what you expect. If that check doesn't make sense for a certain channel, there are ways here to either select channels that you want to do this check on, or even block certain channels where you don't want to do it. So for example, you can block all channels that are RPM and then make the check only work on all the other channels. And then there's the check outliers, which compares the RMS value of your signal and checks whether it's lower than 5% of the maximum absolute amplitude. So basically, if you have a very small RMS value, but you still have a very high maximum absolute amplitude, that basically means that most of your signal is small amplitudes and only some very big peaks are there that don't really influence the RMS value that much. And again, there seems to be some outliers, and it's again something you can check. It might be okay or it might be not okay, but it's a way to find those. The next check is the signal to noise ratio. The idea basically is that if you start a measurement, that you start the measurement while your component is not already doing the test, but it's idling in some way. And then while the measurement is running, you start the test, you end the test, and then you stop the measurement. You see this in the signal like is shown here. So in the beginning, you have something which is, well, lower amplitudes, then you start the tests, and you have higher amplitudes. Maybe there was a pause in between, and then a second part of the test, and then it finishes. If you have a signal like this, it makes sense to check the range in the first part compared to the range of the full signal, because that is the comparison between the measurement when the component was idling with the range of the measurement when the component was under stress, under test. On the other hand, if you have signals that don't do that, if you have a measurement running for a long time and you always take sample, and you take 10 minutes from this machine running, then you don't have that behavior, and then maybe it's the best way would be to switch that check off. The next check is the undersample check. And there also, here's an example. Basically, it checks the difference between two consecutive sample points. And if that difference is larger than 40% of the full range, then the sampling rate should be higher. Or at least it indicates that your measurement might contain frequency that are close to or above the Nyquist rate. In this example here, you see here in the beginning, that's a nice sine wave, and it's sampled pretty well. We have enough sample points picking that up. But then suddenly here, there's a steep change, and whether the frequency in this part is captured correctly, yes, might be the case, but it also could be much, much higher, and the sampling rate prevents you from capturing that correctly. And the signal continues here also with not so nice sine waves, but still this is considered okay. It's smaller amplitudes, the changes between samples are okay. So we will not flag that as a problem, but these large changes compared to the full range of the signal, this is something at least you can look at. And the very last check here, that's just an example how you extend those checks. I just talked only about checks that were done on the time domain or on statistics or with certain checks like spike and drift checks. But you might wonder whether you can also derive data from your measurement and do the check on this. And this one example shows that you, for example, can take all the channels, do a spectrum average, then, for example, extract a certain frequency range from that spectrum, calculate statistics on that extracted range, and do a certain check on any comparison that can use the range of the block. It can have the minimum, the maximum, the RMS, and so on. So whatever you want to do as a check on the block can be done here by using the methods that we have in Process Designer. In this case, I don't really have a good example yet why you would do that. There's something, an example that works, but I don't have a very good explanation why you should do the check. It's really here just as a reminder that you can do checks also on derived data like blocks. And if everything's finished, you will see these results. First of all, the pivot table and then the result indicators. But this is better if you look at this live. So let's go back. I have already in my input data, I have the 4 runs, the time data. My process is selected. I run it. Yeah, I get warnings about the indicators that were deselected and that are not used. That's not important.
So right now it is processing that data, going each of the channels in the 4 runs of data is going through that check, which will give the results in the indicators. Is that right?
Correct. And the results will be in the active analysis. Process Designer works in a way that first it shows you all the results, and then you decide, do you want to keep it or do you want to reject it? So in this stage, we can still look at the data. And so here's this table, and the indicators are shown here. But it's much better to look at that in a different view. So we don't have to look at the process anymore. We just focus on the data. So here I have the results. And as you see here, these are now the results for all the runs. So you can see everything at one glance. To look a bit more and explain how to work with these results, I will focus on one specific run. You can do the same, always clicking here on the all indicators. And I get a list with all the channels here, channel IDs, DOF IDs, and then here you see all the checks that were done. We have no dead signal, we have no drift, we have no flat lines. We have a hardware check. So the hardware check, it's this signal, it's called overload, but it's basically the hardware check of everything. And as you see here, it's a time channel that says there was a problem in the beginning of a measurement. At some point it stopped, and then it came back again for a short time, and it went back to okay. So if I overlay this with all my measurement signals, so we had the hardware checks. That's some generic information. Then we maybe go further. Here we see everything that is 888 is a problem. So we have an improper header. We have some outliers. We have an overrange. We have a lot of signal to noise ratio is low. 2 spikes, 2 times underrange, and a couple of undersampled. So let's maybe start with the spike. What you would do now is you look at the channel where it's happening, C2. I use C2. I use the original channel, the input channel, and I use the index of the spike filter. So that's here spike index. Every column here that is labeled index basically means it's a time channel that is 1 if there's a problem at that time, and 0 if not. Here we see there are 3 spikes in the signal. 2 of them are identified as spikes. And now you can go interactively into these areas, and you can easily see whether you agree, whether it's a spike, or whether you say, no, that's maybe we have to change the parameters to be less strict, or we want to remove that later, or make sure that this is not part of the final validated data. So here, this is the large steep part. This is indicating this is a spike. Can go back, and maybe here, this one is not above the threshold of the spike detection. So this one is not detected as a spike. And here we have another one, which is again the spike. So it's on a very short time, there are large differences, and the differences compared to the differences that happen in the rest of the signal are unusually high. So now this is spikes. There's a second one which basically looks very similar. So you can again look here, there, here. That is, let's just make sure. Yeah, those channels are rather the same. Okay, but they have the same spike, at the same point in time, and it makes sense because Raj introduced the spike manually on his measurement, so it makes sense that it's in both of the channels. Then we also have underrange and undersampled. Let's maybe first look at the undersampled. You already see that the 2 channels that are spikes are also undersampled. So maybe go back to that one, spike, and then also check with the undersampling. The undersampling tells you a bit the same, or something similar than the spike detection, but as you see, it's not exactly the same. But the undersampling means you still have here something that is maybe not captured with your sampling rate correctly. It might be, you just cannot tell. And again, if you, for example, go to the next one, you also see this is still picking up on the same events here. Both are labeled spikes and undersampled. But if I continue to go to other channels, you will see that there are some channels, no spike detection has triggered, but the undersampling has triggered. So there are 2 places where we think it's undersampled, and it's something similar here. So that's really, these differences are larger than 40% of the full range. And then it's really questionable whether you have captured all the frequencies there. And the same here. The nice thing here is really, since you get all this information in the result as where you find this particular problem in the signal, it's very easy to go to these points and check whether this is correct or not. And again, if you check this, there are two options. Either you say, I have to change the parameters to make sure that this is not detected anymore because I think it's okay, or you make sure that this further on is corrected later on in the process by removing that segment or by applying the corrections that we have in the methods. Now look, we can also look at some of the values that are used to detect the improper headers or the underrange and overrange. That's basically, which one? Let us take the C4. So we go to C4, and then I check the limit EU values and the limit EU statistics. And there you see the minimum maximum is plus minus 0.02 G, while the expectation was it's plus minus 101 G. So that's clearly an under range. You can show the signal here. So that's the signal, and let's see what happens if I would change the scaling to plus minus 9. And you see it's basically a flat line. So it's really questionable whether either the limit EU is wrong or the measurement maybe didn't pick up what you thought it picks up. Again, this can be done on many of the channels. Maybe check which one was reported also. Underranged, we also have the overrange in C3. So I go to time signal of C3 and the statistical values. Here you see that it defines a limit EU range of plus minus 10.45 G, but the maximum is 10.7 G. And that's obviously, and it's here, it's somewhere there. It's not really visible here, but it's not that our measurement system is clipping the data at that point. It's more the expectation that you entered and that you get more results. In this case, for example, 10.7 might not be a problem. If the maximum would be 20, then maybe you need to double check whether your expectation and the real measurement is in line. So I think now we had most of them. Outliers is also checked with RMS. Overrange, signal to noise ratio, that is a good one. The signal to noise ratio is indicating for many channels basically, and if I would go to another run and look there, sorry, this one, and then you would even see it's all signal to noise ratio bad. And if you look at the signals, it becomes clear why that is. You remember I said I expect something like this. The measurement starts when the component is idling, there's no test running, and then I start the test. Only then it makes sense to compare the range in the beginning of the measurement with the full range of the total measurement. In this case, these measurements are just happening while the test is running, and you do one sample of 14 seconds. So it doesn't make sense to have signal to noise ratio checked on these signals, even though in this here, there is even, these two are reported as being okay. But in fact, that's wrong. They are still wrong. They only have some spikes in them, which makes this test think, oh, that's fine. We have some small amplitudes here. The overall range is much bigger, so that is okay. So this check only makes sense if you have a measurement that is, as I explained, starting in an idling condition, and then you do the test, and you stop the test, and then you stop the measurement. Only in this case, it makes sense. For this measurement here, I just should disable the signal to noise ratio. It doesn't make sense. So I think I'm through with all the explanations. Okay. I then would hand off to Raj, and you can show how this works perfectly automated after the measure.
Yes. So as Holger beautifully explained, the different checks that can be done to identify anomalies in the data. Now he was showing with the data that has already been collected, and that could have been done with Testlab Classic or Testlab Neo. But what I'm going to show is that how we can use that process that Holger has created live during acquisition. So while taking the data itself, we can set it up such that we can do this check, and immediately after each acquisition, we will get that summary table of indicators telling us whether the channels look okay or not okay. Based on the numbers that were shown, like 1.11, that is 1.11 means the channel looks good, and 8.888 means there may be something wrong. You may want to check. So let's see how that works when we are actually live taking the data, right? For this case, I'm going to use this Simcenter Testlab Neo's time data acquisition module. This is the general purpose data acquisition module. It is equivalent to the signature acquisition in Testlab. Like you want to collect some operational data. You have mounted some accelerometers and microphones. You're running the test at different operating conditions, like vehicle speed or engine speed, whatever, and then you're taking the data. So this time data acquisition is meant for that. And here, what I have also done is that I have incorporated the process that Holger has built for us. So that process I specify, and I include that on the bottom right hand corner where it says process name. I have included that process as part of my run of acquisition. So immediately after the run is completed, this processing will automatically start and will give us that summary table to tell us whether it looks okay or not. In this particular case, what I have is I have the same situation that Holger presented, and that is I have two triaxial accelerometers, A1 and A2. And as you can see, their channels are individually set up. So have acceleration, and I have specified the range that I'm expecting. That is already done. So this A1 accelerometer is I have mounted it on a fan. So the fan is running to simulate operational data. The A2 accelerometer is mounted on a stationary surface on my desk. That is just to show that there is a difference between the two. So A1 and A2 like that. What I have also done is A1Z. It is an ICP accelerometer, but I have disconnected it. So it will show some overload. Let's see whether the hardware checks can warn us about that or not. So the accelerometer is mounted on the fan, and what I'm going to try to do is simulate some spike event. And that I do by tapping close to that accelerometer. So that is like artificially simulating a spike happening. And we will see whether the anomaly detection tool will help us catch that. In this case, I have selected a bandwidth of 1280 Hertz, and that's what we will start with. Now, in time data acquisition, it is laid out similar to what we have in Testlab Classic for signature acquisition, but I think it's a simpler interface. You can get through navigating through the different tabs, and the workflow is in a simpler way. So I go to this measure worksheet, and that is where we will be able to see the signals live for acquisition. Now the name suggests the time data acquisition, but actually you can do monitoring of certain frequency domain calculations also, like overall level, order sections, frequency sections, and such. They are on the top right hand side here. Now first what I'm going to do is I'm going to arm the system by clicking on this button on the bottom left hand corner, and we can see that signals are coming live for the first three channels, which are, remember that the accelerometer is on the fan, mounted to a fan. And we can see that there is some 2.7 and then 11 meter per second square in terms of that, right? That is a level. We can already see on the bottom right hand corner, one channel is being detected as overload. That is the Z channel of the first accelerometer that I had purposefully disconnected it, right? So it is correctly indicating that. And then the bottom three channels are the second triaxial accelerometer. That is showing low vibration levels because it is not mounted on the fan. Okay, so we can see that live. Now I'm going to start the data acquisition. Okay, so then we can see the signals live as they are coming through, and we see some operational data. Things look okay. This channel looks suspicious, the blue one, because it's showing some levels which are low, and shape of them is not so periodic because I'm measuring that on a fan. So I would expect something more regular, I would guess. And then what I will do is I'm going to tap it near that accelerometer, which is mounted on the fan, and we can see the increased vibration levels for that channels on the top one. And then once my acquisition is completed, then I'll click on the stop button, and at this point it will start to do the processing automatically. So you can see that in the bottom part, it is currently doing the processing. It is going through the same indicators calculations that Holger has shown us. After the run is completed, even without disarming the front end, now I want to look at the results. And I click on this run one, and here it shows me the summary of the indicators, and I can go there and check. So this is the summary of the indicator table. And we can see certain things. Most importantly, what we are looking at is a spike. And that is something Holger pointed out. In this case, I can see that the accelerometer X channel and the Y, which would have seen the spikes, those are correctly indicating that there was indeed spike for that. The other important thing is that the A2, it is not showing any problem because it didn't experience any spike. Only the A1 accelerometer for these two directions, that detected that should have shown there's a problem, and it correctly shows us that. We can go back and take a look at the signal to see where that has created a problem. So if we look at the A1X, like we can look at the time history, and then also we can look at indicator for that, which is spike index channel. And we can see this is bottom part shows the actual measurement of the channel, and then the top part is showing the index, like where all it said there is a spike. And as Holger explained, not all events are spikes, right? And it is up to us to tell the tool what we consider as a spike. Now this, based on our default definition, this one is not considered a spike, and the next few ones are considered spikes. If that meets our criterion, then that's fine. If it is not, then we have to check our definition for what we consider as a spike and accordingly change that. Now, just as a further check, what I want to do is I want to go back here to the active run, and I want to look at the channels. And this time I'm not going to do any impacts or any spikes. I'm not going to introduce any spikes in the data. So let's see how that result comes out to be. So I click on the start button. It is starting the measurement, and I can see the measurement duration on this side on the bottom right hand corner. I'm collecting like the 10 seconds of data. Then I click on the stop. And this is a new run that was just calculated, run 2. It is doing the processing automatically after the acquisition is completed. And then I can check it. I can check how the results look out to be. So then I go back here to the indicators, and this time I don't see any spike for any of the channels. And this is because I did not artificially introduce the spike. There you go. This is a good check for us to confirm that things are going okay. So with that, I think that pretty much brings us to the end of this webinar. I want to point to you that also that we are using the built-in methods within the process designer. I'm in the processing tab. I have loaded that process, and we are using different methods available, which are these blocks that can help us identifying the various anomalies here. So like Holger presented for the spike filter, we defined the parameters for that here. If we are not sure what exactly that does, you can click on this documentation, and we can look at what is the definition for the spike filter, what is considered as a spike, and what is the mathematical formulation for that. Make use of that help, because in my opinion, the Testlab Neo documentation is really helpful. Again, the default parameters that we specified for this anomaly detection may not work in all situations, but the good thing is that you can customize it whatever your particular scenario is. What we consider a spike in one situation, that definition may not be applicable for all situations. So you want to check it, you want to use it and see whether that is indeed what your particular situation calls for. So it's not a black box. That is the beauty of it. You can adapt the parameters to identify what you consider as an anomaly. All these methods are pre-built in, but you can modify them. And that to me is a wonderful thing from an engineering standpoint of view.
Yeah.
Thank you.
Thank you.
Bye.